In this video, I'm going to be looking at section 4.2. This deals with two theorems, Rolle's and the mean value theorem. All right, the first one we're going to look at is Rolle's theorem. Rolle's gives you the conditions guaranteeing the existence of a maximum or a minimum in the interior of a closed interval. So here's the idea. It's pretty obvious when you see it. Okay. So if you have a function that is continuous on an interval and differentiable within it, and you know that, let's look at this first picture on the left, and you know that the value of the function at A equals the value of the function at B, which means the height of these 2 points, the beginning and the ending point, are at the same height. So if you know the function is continuous on this interval, and you know it's differentiable within it, and these 2 points are at the same height, then you know it has to reach either a high point or a low point in between there. Right? So there's going to be at least one spot in between A and B, and that's what they're talking about when they talk about find the C value. There's going to be some number in between A and B, okay, that's within that open interval from A to B, where the value of the first derivative at that point is going to be 0, which just means the slope of this line right here is going to be 0. Okay? And the value of the first derivative at that point is what they're talking about here. Okay? So over on the one on the right, we have a situation where the beginning and the ending points are at the same height, and the function is continuous. I don't have to lift my pencil there. But at this spot right here, f is not differentiable. Like if I did the formula for the first derivative there, it would be something that had a treble spot. So there's no derivative there. It's got that sharp point. Okay, so Rolle's theorem would not apply on this. Even though it is a maximum there, you don't know it because of Rolle's theorem. Okay, doesn't apply. Okay. All right, so when you're asked on these, when you're asked to determine if Rolle's applies and then use it to find any value of C in the open interval that causes the value of the first derivative to be 0 there, be sure to start with whether it can be applied. So first thing you want to notice here is that f is just a parabola. It's a polynomial. So we know that you want to comment on the fact that f is continuous on the interval, okay, because it's continuous everywhere, and we know it's differentiable on that open interval because it's differentiable everywhere. Okay, so one more thing though you have to check is the value of f of 2 going to be the same as the value of f of 6? So you plug in 2 and you evaluate the function at 2. And for that one, you get 4 minus 16. So that's negative 12 plus 5 would be negative 7. And then you got to check the value of the function at 6. When you do that, you get 36 minus 48, which is negative 12 plus 5, which is also negative 7. So it meets all those conditions that have to be met. It's continuous on the closed interval, differentiable on the open interval, and f of 2, these are the same value. So it checks that. So if you know all of that has been met, then you can actually do the work. So now what you're going to do is you're going to find the derivative of the function. So it's a nice polynomial, so that's pretty quick. You're going to set that equal to 0 and solve. So you get x equals 4. And then notice that 4 is in the interval from 2 to 6. So 4 is that C value that they're talking about in Rolle's theorem. So C equals 4. Okay. So your job on this one was to find all the values of C in the open interval from 2 to 6 that make the value of the first derivative at that spot equal to 0. Okay. All right, so here's another one. Again, this one, if I were to multiply it out, would just be a polynomial. In fact, I might do that before I have to evaluate something or before I have to do the derivative. But to start with, I know it's going to be continuous on that interval because f is continuous everywhere and differentiable everywhere because it's just going to be a polynomial. If either of those failed, you would just say Rolle's does not apply, even though you might be able to find a min or a max. It wouldn't be because of Rolle's theorem guaranteeing it. Okay, now I'm going to do f of -2. And I could multiply through first if I wanted to, or just plug in a -2 for x here. When I do you notice how that's 0? And so 0 times anything is going to be 0. And f of 4, when I plug it in, makes the other factor 0. So for the same reason, if this is 0, the whole thing would be 0. Okay, so these are equal. These are equal. So that's the third thing. It has to be continuous, differentiable, and those two values have to be equal. Now, once it is, then I want to do the derivative. So I have options here. I could multiply everything out and just use the power rule, or I could do the derivative by using the product rule if I wanted, thinking about that as u and that as v. So 1 times x plus 2 squared plus 2 times x plus 2 to the first power, and the derivative of the inside is just 1, but don't forget to multiply by x minus 4 as is. So this is your u prime, this is your v, this is your v prime, this is your u. Okay, or you could multiply out and have done it that way. All right, so on this one, at this point, you could multiply out. I might do factoring though, because see, here's an x plus 2, and so is there an x plus 2. So I might just try that to get it worked out. So x plus 2, if I factor that out, I would have another x plus 2 left in that from that first term. Then from the second term, I'd have a 2 and an x minus 4. Again, you could just multiply stuff out if you wanted to. So here I would have x plus 2, and then here I have x plus 2 plus 2x minus 8. So 3x minus 6. Oops. I was thinking about how that could be factored, but let me write it. 3x minus 6. This is x plus 2. And if I wanted to know where that was equal to 0, I could set those equal to 0, and I'd get a -2 from there, and then add 6 divided by 3. I'd get a +2 from there. All right, now -2 is not within the interval, so that's not the c they're talking about, but 2 would be. So that's the c that is guaranteed to exist by Rolle's theorem. All right, so let's try number 3. So number 3, it might help you to realize that's really a cube root of x that's being squared. Okay, still f. All right, so that's going to be, f is continuous everywhere. There's no problem plugging in negative numbers 0 or positive numbers. So that condition is met. To tell whether it's differentiable might help to go ahead and do the derivative. So let me do that, and I'm looking at the original form that had the exponential notation. I'm going to bring down the 2/3, take x, subtract 1, get a -1/3. The derivative of 1 would be 0. So this really is 2/3 cube root of x. And so I have a problem, don't I? F is not differentiable at x equals 0. Okay, and that's x equals 0 is in the interval we're talking about. So Rolle's doesn't apply. Okay, so these conditions that I'm checking over here are telling me that that Rolle's applies. Rolle's applies. Okay, All right, so we don't go any further. All right, on this one, do you see how f is not continuous at x equal 1, and x equal 1 is in the interval from -2 to 2, so we know Rolle's doesn't apply. We stop. Doesn't mean there's not a min or max somewhere. Just means it's not guaranteed by Rolle's theorem. All right. Now this is a trig function. Okay. So we know sines are differentiable everywhere, and 3x is differentiable everywhere. So that composition of those would be differentiable everywhere. And remember, this means really sine of 3x. 3x is the input to the sine function. Okay. So we can comment on the fact that f is continuous everywhere. So it's continuous on that interval. And if you did the derivative of that, derivative of sine is cosine of the same input, and then the chain rule says go ahead and take the derivative of the inside function. So you'd get a 3 cosine 3x. Okay, so f prime is differentiable. I shouldn't say f prime. F is differentiable everywhere because f prime has no trouble spots. Okay. And then I need to check f of pi over 2, which would be sine of 3 pi over 2 when I plug it in. And I need to check f of 7 pi over 6, which would be sine of 3 times 7 pi over 6, which equals the sine of 7 pi over 2. Okay, so let's think about those two. So 3 pi over 2 would be here. The sine would be -1. And then let's think about 7 pi over 2. So if this is 3 pi over 2, when I go to here, that's 4 pi over 2, 5 pi over 2, 6 pi over 2. Wait. I didn't count that right. No, I did. I did count that right. So we wind up at that same spot. So 7 pi over 2. Okay, so that would really wind up being 1, 2, 3, 4, 5, 6, 7 pi over 2 would wind up being right back there. So it also has a value of -1. So we got it being continuous, differentiable, and these are equal. So Rolle's applies. Now our job is to find those values of C. Okay, now this one's going to be a little tricky because of the 3 with the x. All right, so we know what we want here is we want this to equal 0. Okay, so we want 3 cosine of 3x to equal 0. So we have to think about where that happens. Where is cosine 0? So we see that it's going to be 0 at pi over 2 and at 3 pi over 2. And as you wrap around, it'll be equal, cosine will be equal to 0 at any of those. Okay, so we need the cosine of 3x to equal 0. And we know that that happens when this angle right here, the cosine of an angle is 0, when you hit pi over 2, 3 pi over 2, or any angle that's going to wind up at one of those two places. So we know that 3x would wind up equaling pi over 2, but then you could wrap from pi over 2, you could add pi, so this much. You could add pi or subtract pi and get to another angle that would have a cosine of 0. So we're going to add any integer multiple of pi to that. Okay. All right, so now you're looking for x, so you have to come in and divide by 3. When you do, or take a third of everything. When I take a third of pi over 2, that's going to become pi over 6. 1/3 times So if I do 1/3 times pi over 2, that's pi over 6. And then I need to take 1/3 of this, or divide by 3 there as well. Okay? Because what you do on these multiples, these problems where you got a multiple of an x value, is you have to think about then, well, what if n were equal to 0? So if n were equal to 0, you'd get pi over 6 plus 0 pi over 3, which would be 0. All right, now look at your interval you're working in. All right, that's not going to be the c value. If we let n equal 1, we'd have pi over 6 plus 1 pi over 3. That's pi over 6 plus pi over 3. Okay, pi over 6 plus pi over 3. That's the same as, this is the same as pi over 6 plus 2 pi over 6. This would equal pi over, that would be 2 pi over 6. That would be pi over 2, because you'd get 3 pi over 6. Okay, well, that's right on the end of the interval, but it's not within it. Okay, let's try n equals 2. Okay. When we do that, we'd get pi over 6 plus 2 pi over 3. Okay, so multiply top and bottom by 2, you'd get 4 pi over 6. So that would turn out to be 5 pi over 6. Now 5 pi over 6 is within that interval. So that's going to be a c value that we know has to exist. There's one. And then watch, if I go to n equal 3, I'll have pi over 6 plus, and I'm putting in 3. So I'd get pi over 6 plus 3 pi over 3, which is pi. Okay. So that'd be 6 pi over 6 plus 1 pi. That's 7 pi over 6. And there we are at the end of the interval again. So the c we're talking about that we know must exist is 5 pi over 6. All right, I think on this one, what you're going to struggle with the most is the trig part of how you solve these kinds of things when you have some multiple of x in there. And I think sometimes people forget this part of it, how you need to think about pi over 2 plus any multiple of pi would give you, you would wind up getting a cosine that's 0. And you need to add that multiple of pi before you divide by this 3 right here. Okay, so you can get all the possible answers to the question. Okay. I'm going to stop this, and then I'll do the mean value theorem in the next video.